Greetings to you. This lesson is based on momentum and conservation of momentum. Without wasting time, let us go to our slide presentation. I'm going to share with you our slide where we discuss closely the aspects of momentum and conservation of momentum. And this topic is based on the Cambridge IGCE physics syllabus. Let's go on to define momentum. Momentum is defined as mass multiplied by velocity. We usually use a symbol P. And when we do that mathematically, our equation is given by P equals to mv, where P is the momentum, m is the mass of the object, v is the velocity of the object. And momentum is a vector. It has both magnitude and direction. Let's go on to the principle of conservation of momentum. The principle of conservation of momentum states that if no external forces act on a system of interacting objects, the total momentum remains constant. And an example of an interaction is a collision, and that's what we are going to discuss in this lesson. There are other types of interactions that we'll see in lessons that will follow, and the equation that we are going to build is going to be modified accordingly. But a collision helps us to model a generic equation for the principle of conservation of momentum. So I've got here a diagram that shows the collision of two objects before and after collision. The two objects have masses m1 and m2 respectively, their initial velocities being u1 and u2 respectively, their final velocities being v1 and v2 respectively. When you use those terms, the generic equation is as shown here, where the terms are as defined. This is our generic equation, meaning that it is generally applicable. It's just a general equation which shows the principle of conservation of momentum mathematically. Now let's go to the application of this equation in certain specific situations. There are two scenarios that happen after two objects collide. Scenarios one is when the two objects separate, and scenario two is when the objects stick together. Scenario two, they stick together. In scenario one, the applicable equation is the generic equation. In scenario two, we have got a modified equation for the two objects. And V is their common velocity after collision. V is their common velocity. Now, let's now see how we apply these equations in solving problems. I've got here an example worksheet. Let me stop sharing the slide presentation and share the examples worksheet. So in this worksheet, we are going to apply these equations. Now, example one, and we are going to work together these problems. We are going to be working together. In example one, the two objects collide, and they are shown in the diagram. They collide and they stick together. So the applicable equation is the one in which they stick together. That is the applicable equation. So the first thing when solving an equation is to write down the applicable. When solving a problem is to write down the applicable equation and then to substitute into the equation. And here we haven't been given the mass, but they have got same mass. Solving these problems requires some good knowledge about our algebra. And we'll use mass M for the mass, which hasn't been given. And we will also indicate direction. Let's indicate direction to the right as positive. And when we do that, it means the object Y we have a velocity of -3. So this simplifies to 5m minus 3m equals to mc. And when we solve this, we need a good knowledge about algebra. And 2m into 2m is 1. So the velocity is 1 meter per second. And the option is B because the answer is positive, meaning that the object moves to the right. So this is how we apply this equation. I'll also just leave to you to try and build the equation for question 2, and then you try to solve it. I'll just give you some time to try and solve the equation. And you are quite right that the applicable equation is the same as the one that we used in the first problem. Because the objects stick together or coalesce, they stick together. So then we go on to substitute. In this presentation, I'm just using the word application, but in the actual lessons, we will use an interactive whiteboard where the student also works on the board like I'm doing. It's interactive. It can be used by both parties, the learner and the teacher. So our answer would be 3.5. I'm sure you can see that it becomes 14 divided by 4, which simplifies to 3.5. All right. I'll also just give you a chance to be looking at question 3. And in question 3, a visitor to a fairground throws a soft object of mass 0.12 kilograms at a coconut of mass 0.848 kilograms. The soft object stops moving when it hits the coconut. In order to dislodge the coconut, it must be made to move at 0.10 meters per second. And just take note of that. The coconut's velocity, initial velocity is not given, but from the facts given, it is reasonable to assume that it's actually at rest. I'll just give you time to formulate the equation and substitute and solve it. You were quite right that the applicable equation now, since they separate, it is the generic equation. then we substitute. And in this case, we do not know the velocity of this soft object. And like I said, it is reasonable to assume that the coconut is at rest. It stops moving, so it comes to rest. But the coconut moves at 0.1. Let's just create more space for working here. So this is 0.12 U1 equal to 0.048. And like I said, we solve our answer will be 0.4 if we use our calculators. So our option will be B. In this case, there was no real need to show the directions as I have done in question 1. The assumption is that they move in the same direction in question 3. In question 2 also, it has been stated that they are moving in the same direction here. So there was not really much need to show their direction, and also that we are just calculating speed. If they are moving in the same direction, so they can have positive momentum each. So take note that we need to specify direction where applicable. I'll give you a chance to just try out question 4. And as before, I think you are right in assuming that the two objects, since they separate, all right. And then we go on to substitute. And the second ball is of mass 0.1 and it's at rest. And the first ball, we want that speed, with the final speed with which it moves after collision. And the second ball moves at 0.5 meters per second. This simplifies to 0.8. And this is 0. This gives us 0. And solving this requires quite some competence in algebraic equations. It requires good competence in algebraic equations. And this gives us 0.1875. But you can see that in the options provided, we do not have 0.1875, but we have got 0.19, which is 0.1875 rounded to 2 decimal places. So in addition to having knowledge about how to apply these equations, we also need a good mathematical background, rounding off and solving algebraic equations. And it is quite important to go through those concepts. We can also go through them together if need be. Raise those issues with me if you have got challenges in solving algebraic equations. Then we go to a walkthrough algebraic equations. They are very important in solving problems relating to momentum. All these problems were taken from IGCE physics. The syllabus concerned is 0625. They were taken from the Cambridge examinations papers. I've sent through the practice worksheet for your homework. You go through it and send me an email where you have got challenges so that we deal with those problems. Thank you very much for attending this lesson. Thank you so much. So this brings us to the end of the lesson. Please try as much as possible to do your homework as soon as possible. Thank you so much.